Welcome to chapter 18. This is from a different text we'd used in years past. So after chapter 18 covers the same information, amino acids, proteins, not enzymes, right? So we'll be talking about amino acid-based peptides, proteins, protein hydrolysis and denaturation. We will not be talking about enzymes. That's the next chapter. Okay. So, amino acids. These are compounds that have an acid group and an amine. So acid red, base blue, amines are organic bases. These amino acids are the building blocks of proteins. We'll talk about those more in a little bit. But first thing I'd like to say is that these are alpha amino acids. So what do we mean by alpha amino acids? So alpha amino acids. If you remember, we had a fatty acid, let's say, and there's 1, 2, 3, 4, 5, 6, 7, 8. Remember we talked about these and we said, all right, well, the last carbon of a fatty acid we refer to as a omega carbon. It's the last letter in the Greek alphabet. First letter in the Greek alphabet is alpha. Now this carbon here with the carboxyl group is not the alpha carbon. It's this carbon that's next to it. Okay, so it'd be alpha, beta, gamma, delta, and so forth. So they correspond to carbons 2, 3, 4, 5, and whatnot. So we're really looking at carbon 2. All amino acids that get incorporated into proteins are alpha amino acids, meaning the second carbon, the carbon next to the acid group, has the amine on it. So the alpha is referring to where this amino group is. Right? So where is that amino group? Here's the carboxyl. Here's the alpha carbon. The amino group is attached to it. Okay? So what they're showing you here is the very simplest of all amino acids, glycine, and then some just general amino acid. All right, I've already talked about the carboxyl group, the amino group, the alpha carbon. This group here, right? Each amino acid contains a different side group. Now there are 20 different amino acids, so there are 20 different side chains, this R group. So 20 different R groups or side chains. R groups. For a simplest amino acid, that R group is nothing more than a hydrogen, right? So most amino acids are going to have a hydrogen attached to them, okay? And then some side chain on this alpha carbon. It says here, amino acids are ionized in solution. All amino acids, even the simplest glycine here, is also a solid. They're ionized in solution, and they're all solids at room temperature. Let me write this down. All solids at room temperature, and they actually form what's called an internal salt. We'll talk more about that in a little bit later. Form an internal salt. So salts, if you remember, it's a combination of an acid and a base, something like sodium chloride. The acid was hydrochloric acid. That's where the chloride came from. The salt was the sodium hydroxide. That's where the sodium came from. The salt is a cation and an anion, right? So we have an ionic bond between a positive and a negative charge, right? So that's what I'm talking about, a salt. So you see that here with amino acids, right? When we say it's ionized, the amino group is positively charged. Again, nitrogen normally forms 3 bonds when it's in group 5. It has 5 valence electrons. It needs 3 more. It gets those from each of the 3 hydrogens. So there's ammonia. It has an unchaired pair. The ammonium ion has an extra hydrogen and a plus charge. So remember, when nitrogen forms 4 bonds, it has a plus charge. So there's 3 hydrogens. The 4th one is to this carbon, so it has a plus charge. The carboxyl group, actually this is a carboxylate, is also ionized. So here's a carboxyl group. Let me just draw this like this here. Okay, let me draw this hydrogen. This is the acidic hydrogen, right? And this hydrogen can come off. So if we were going this way, right, this hydrogen comes off. It ionizes, right? There's that hydrogen comes off, it ionizes, becomes C. Let me draw it this way. C double bond O dash O minus. Right, so that's what this carboxylate is. All right. Well, that hydrogen comes off, right? Where's it going to end up? Well, it can bond to the unshared pair of electrons on a nitrogen here, and we get go from NH2 to NH3. So this form here, right, is how you normally see amino acids, right, in this ionized form when it's in solution. All right, now I had mentioned there are 20 different amino acids, 20 different side chains. Here's actually I should mention this too. I forgot to mention this. What they have in blue here, right, in blue here, this is what we call the alpha carbon backbone. Right, the alpha carbon backbone. All amino acids are going to have, I shouldn't say all, but maybe one, are going to have, and you'll see that one exception, are going to have the same alpha carbon backbone. And it's just the side chains that differ. Right? Now, I said there's 20 of them. You do not have to memorize either the names or the structures of those 20 different amino acids. It would be nice if you familiarize yourself with the names. So there's alanine, serine, aspartic acid, lysine. They each have these different side chains, and some are non-polar, right? So it's just like an alkyl group, right? A hydrocarbon, like say a methyl group. Some are polar. They have OH, right? So this is like an alcohol. Some are acidic. Here's the alpha carbon backbone. Here's our alpha carbon. This is their carboxylate. We have another carboxylate here. So the side chain also has an acid, so it's an acidic side chain. And then some are basic, right? So we have an amine on the side chain. So you don't have to memorize the names or the structures. What you have to do is, once you look at the structure, be able to figure out, okay, where's the alpha carbon? Where's the carboxylate? Where's the amino group? What's the side chain like? Here's the side chain, and then classify it as either non-polar, polar, acidic, or basic. Okay. So let's look at each one of these different types of amino acids. So as I mentioned before, glycine, the side chain for glycine is just a hydrogen. It is the simplest of all amino acids. Alanine, just a methyl group. Oh, by the way, these are the non-polar amino acids. So we have non-polar, you can say hydrophobic amino acids. So mostly they are alkyl chains, right? So we have valine here. Looks like a V for valine. No, it's like an isopropyl group, right? We have a leucine, right? So this is like a isobutyl group. This is also 4 carbons, but instead of being branched on the last carbon, it's branched on the first carbon here off the alpha carbon. So they're kind of isomers of each other. This is isoleucine. We have a phenyl ring. I don't know if you recall when I talked way back when about benzene. Benzene, when it's named as a substituent, right? So if we had like the parent alkane here, and we're going to name benzene as a substituent, a branch on that, we named it as a phenyl group, so that's what you see here. Alanine just has a methyl group. Here we have a phenyl attached to an alanine, so hence phenylalanine. Methionine is something quite different. Methionine has a heteroatom sulfur, but carbon and sulfur actually have the same electronegativity, so there's no polarity here even though there's a heteroatom. Skip proline for a minute. And then there's tryptophan. Now tryptophan has a nitrogen here. this is, well, I won't get into the name of this kind of ring structure here, but it's really not all that polar. We've got a benzene ring plus a couple more carbons. There's the methyl group of alanine here. Anyway, this tryptophan is also not polar. Now, proline is a bit different. Proline, and by the way, it's pronounced proline, not proline. Proline is the name of a trucking company. Proline, I think they also make golf clubs. I think there's a Proline sporting goods. But proline is the amino acid. And you notice here, this side chain comes up and then wraps around and then bonds to the nitrogen. So remember I said all of these alpha carbon backbones are going to look the same, except for proline. Because proline, and let's just take an easy one here. This is going to be a primary amine. Right, if we go back to the chapter on amines, right? This nitrogen has just one carbon-carbon bond, and they're all like that, except for proline. Proline is the only one that is a secondary amine. So it's rather unique in that regard. And had you done the chromatography lab that was scheduled, you might have, and I won't get into the details, but proline, because it's a secondary amine, reacts different than all the other amino acids. A couple other things to mention here. They have these numbers here: 5.7, 6.3, 5.9. What these values are, something called the isoelectric point. I'm going to write it as Pi. It's usually referred to as Pi for point isoelectric, but it's we usually say it's the isoelectric point. And I'll talk more about this later, but right now, if you want to refer back to these later, you can see that these are all about the same, all around 6.0, and that's I'll just say here about 6.0. We refer to this as a neutral. Now, obviously, this has something to do with pH. Obviously, a neutral pH is 7, but 6.0 is close enough. We're going to say these are neutral. All right. Last thing. These amino acids have three-letter abbreviations: glycine, GLY, alanine, ALA, valine, VAL, tryptophan, TRP, proline, PR, whatnot. All right. You don't have to know. Like I said, I'm not going to test you on memorizing the names or the structures. Certainly not the three-letter abbreviation. But what I want you to be aware of is that there's also a one-letter abbreviation. So glycine is G. Alanine is A. There's another amino acid, cysteine, it's C. There's another amino acid, threonine, is T. Now the reason I bring this up is because you might be familiar with DNA. And we didn't cover that chapter in lecture, but I think that was actually chapter, the next, I think maybe chapter 20, I'm not sure. DNA has 4 different, what we call bases. And I won't get into the details here, but they go by the abbreviation G, A, T, and C. Well, we have a G, A, there's also a T and C here. But DNA, that's all they have are these 4. Protein has 20. So, right, valine is V, phenylalanine is not P, proline is P, phenylalanine is F, because why not? It starts with a F sound. Methionine is M. Tryptophan, I like this one, it's a W. I won't get into why that is, but anyway, if you see a sequence of one-letter abbreviations and it contains something other than GATC, then you know it's protein and not DNA. DNA will just have these 4. Proteins are made up of 20 common amino acids, and they all have one-letter abbreviations as well. Again, don't have to memorize them, just something interesting to point out here. All right, now we have some polar amino acids, right? So these are going to be hydrophilic. They're polar, hydrophilic, but neutral. And what we mean by neutral is neither acidic nor basic. So you can look at these isoelectric points, these PIs, 5.7, 5.6, 5. Again, they're called neutral, but really they're not neutral with regard to a pH of 7, but they're relatively neutral compared to the acidic amino acids, right? We have two of those, aspartic acid and glutamic acid, right? So essentially for aspartic acid, we have an acetic acid molecule as a side chain. For glutamic acid, we have propionic or propanoic acid side chain, a 3-carbon acid side chain. And glutamic acid, you might be familiar with MSG or monosodium glutamate. Monosodium glutamate. What that is the monosodium salt of glutamic acid. So if we had a sodium ion here, this would be monosodium glutamate. I'm sorry. Confuse me. The acidic side chains, or the acidic amino acids, are these two. The basic amino acids, there's these guys. Basic. So these all have amines as their side chains, right? See a lot of nitrogens here, and of course their isoelectric points are much higher. Now again, we consider them basic. Now 7.6 is actually pretty close to a neutral pH, but it's basic relative to these others. If neutral, neither acidic nor basic ones are around 6, then if we're at 7.6, this is more basic. But anyway, so we have histidine, lysine, arginine. These are the basic amino acid side chains, the one with the nitrogens in them. Now I want you to be careful here. These here that have these amines, right? Notice, but here's a primary, like a primary amines here. Notice this guy, just one carbon-nitrogen bond, but this carbon also has, let me put it in a little bit clearer here. This is a double bonded to an oxygen, right? Double bonded to an oxygen. These two guys, right? Don't get fooled here. Yeah, they have an amine, but this nitrogen is not the same as this one. These guys are amides. Right? What is an amide? Well, this would be asparagine. Well, if you took aspartic acid, right, 2-carbon, like acetic acid side chain, 2 carbons, that's what we have here, and reacted it with ammonia, you'd go from aspartic acid to asparagine. So you're essentially neutralizing this acid with an ammonia here, and so this is not a basic amino acid. It's polar but neutral. Likewise here, glutamic acid, right? 3-carbon acid side chain. We react this with ammonia. We get the 3-carbon amide side chain. We go from glutamic acid to glutamine, right? So monosodium glutamate is the sodium salt of this. Glutamine is not. Glutamine is an amide. Amino acids are stereospecific, and what we mean by that is, actually, let's go back once here. If you look at these amino acids, each one of these alpha carbons, right, each one of these is chiral, all except for one. The one amino acid that is not chiral is the simplest one I talked about, glycine, where the side chain is just a hydrogen. Well, the alpha carbons all have a hydrogen. If we have another hydrogen here, then it's not chiral. Right? So all amino acids are chiral, except for glycine. And actually, while I have it here, let me just, we're used to thinking of these, well, I don't know if we're used to it or not, but we talked about Fisher projections. Right, so in a Fisher projection, right, we just put a little cross here. We don't put the carbon in that's chiral. Well, that's the alpha carbon. Let's use alanine for example. Okay, so here we have the carboxyl group, the alpha carbon, the amino group. In a conventional Fisher projection, right, the nitrogen that's attached to this alpha carbon is always going to be on the left. So here we have the nitrogen, here's the hydrogen. The side chain is down here. This is our CH3 side chain of alanine. So okay, this is our R group. So all amino acids are going to have this structure where the amino group is on the left in a Fisher projection. That makes these guys L amino acids. Here again we see the Fisher projection. Here is alanine. Here's alanine. Don't have to worry about the dashes and wedges. Really all you need to know is that all naturally occurring amino acids are L. So you can go to drugstore or whatever and buy amino acids as supplements, and sometimes they'll sell you a mixture, what we call a racemic mixture. It's a DL, which is we call a racemic mixture. It's 50% of the D and 50% of its L enantiomer. It's a mirror image. But oftentimes you'll also find it purified, so we have just L. So they'll sell you L-leucine, right? Or L-tryptophan. This L is referring to where this guy is where this amino group is in the Fisher projection. Notice here we have the mirror. In the mirror, if the amino group is on the left, here in the mirror, it's going to be on the right. So this is the D isomer. It's on the right. So these are not natural, not incorporated into proteins. These are the natural ones. Down here it says ethyl ester. So you can read this here. It says ethyl ester HCl for instant absorption. So this has something to do with how amino acids are prepared so they're absorbed better. So let me just talk about what we mean by this ethyl ester. So if we look at, do leucine here. Okay, the side chain for leucine, if you recall, was 4 carbons, look something like that. Okay, an ethyl ester, well, first it says ethyl ester HCl. So the HCl, the hydrogen goes to the amino group here. Acid reduces the base. This becomes, right, positively charged. And then we have chloride as the counter ion. So that when they say HCl, that's what they're talking about here. So it's a chloride salt of this. We have an ionic bond between the chloride and the ammonium here. The ethyl ester, remember esters is a combination of a carboxylic acid plus an alcohol. So if it's ethyl ester, we're using, in this case, the ethyl alcohol. So instead of having a carboxylate here, where it would normally be negatively charged, what we have is like an ethanol molecule attached, right? So this is the ethyl ester. As I mentioned earlier, all amino acids are solids at room temperature. They exist in internal salts. And so one part of the molecule, you can kind of think of it, doesn't really work this way, but good enough. One part of the molecule, the acid, reacts with the base. We protonate the amine, we get the ammonium ion. The base has been deprotonated, so we have a positive and negative. And what that means is we could have another amino acid forming an ionic bond between, here's the ammonium of one amino acid, the carboxylate of another, or the carboxylate of one amino acid forming an ionic bond to the amino group of another. And so we have these ionic bonds that exist as an ionic solid, right? That's what we mean by an internal salt. Another term here is Zwitter ion. Okay, maybe you've been to a Brewers game, and I don't know if they still do this. It's been years since I've been to a Brewers game, but they used to sing this like German drinking song, Eins, zwei, drei. I can't remember how it goes, but zwei, they're counting. Eins is 1, zwei is 2. A Zwitter ion means 2 ions. German for essentially 2 ions. Zwei, Zweiter ion, Zwitter ion. We pronounce it as Zwitter ion. It has the ammonium ion and the carboxylate. right? That's what you see here. This is a Zwitter ion, the ammonium ion and the carboxylate. I mentioned the isoelectric point, the pi, right? The pi, this is the pH. What is the isoelectric point? This is the pH at where the Zwitter ion exists. What do we mean by that? Well, if we were, well, you'll see this in the next slide, but we could say increase the pH, make it more basic, or we could decrease the pH, make the pH more acidic, make the pH go down, and that's going to affect the charges here. So we'll see that on the next slide. 1, 2 protein, no, 1, 2, 3, right? If we decrease the pH, how can you decrease the pH? You can add acid, plus acid. You're adding hydrogen ions. What happens? The hydrogen ion is going to, hydrogen ion is positively charged. It's going to bond to or protonate this acid group. So, right, it's been protonate the acid. Now, what about the base part, the ammonium ion? Well, it already has, this nitrogen already has 4 bonds. It can't form 5, right? It's already has its extra hydrogen, so it's not going to change. It's just the hydrogen here gets added, right? So at low pH. At the isoelectric point, so this is actually glycine. So I think the isoelectric point here, the pH, say is about 6.0. pH is lower than 6.0. We start putting more and more hydrogens on here. We increase the pH. How do we do that? We add base. Right. That increases pH. So you're adding hydroxide ions. What happens here is a little bit more difficult to, actually this plus charge actually should be down here, right, on that nitrogen. So what happens here is the hydroxide ion that we're adding, right, because we're adding base, the hydroxide ion reacts with one of these hydrogens to form water, OH plus H, because that's H2O, water, HOH, right? So we're losing one of these hydrogens, H3 becomes H2, and then it loses this positive charge, right? Nitrogen now has 3 bonds, 2 to the hydrogens, 1 to a carbon, so it's neutral. What happens to the carboxylate? Well, nothing, right? We're at a higher pH, we're not going to affect this. This is in fact the conjugate base of that. So at high pH, it's going to have, another way to think about this, at a high pH, the charge is -1. At the pH near the Zwitter ion, we have a positive charge. Let me put this as black here. A positive charge on the nitrogen, negative on this oxygen. So plus and negative. What's the charge? Well, they cancel each other. So the net, I should write here, the net charge is 0. At a low pH, we've added acid. What happens? We have a plus charge, right? So at low pH, the net charge is +1. Well, how did you get to a low pH? We added hydrogen ions. Hydrogen ions have a plus charge. The amino acid has a plus charge. At the isoelectric point, it's neutral, right? No charge. The positive and negative cancel each other out. And at a high pH, well, how do we get to a high pH? We added hydroxide ions, right? The hydroxide ion has a -1 charge. So hopefully that can remind you of what's going on with the isoelectric point and the form of the amino acid at various pHs. Now, we're only dealing with glycine here, and we haven't talked about anything that has an ionizable side chain, but let me just mention here acidic and basic. I'm going to just abbreviate amino acid AA. Amino acids have ionizable side chains. Ionizable side chains. And I won't get into the details here, but they can still have Zwitter ions. So at the pi, you're going to have a positive ion on the nitrogen, a negative on the carboxylate, but the ionizable groups will not be ionized. And so they, just so you know, they still have, I should say here, but still have the Zwitter ion at the pi. Next we'll talk about peptides and polypeptides and how we put these amino acids together to make proteins.